So as far as artificial hip implants are concerned, structural integrity is very important because they work under very unfavorable exploitation conditions. And no matter how well they are made, eventually adverse effects like corrosion and especially fatigue will get the best of them, causing failure. And our goal here was to see how these different conditions affect the actual fatigue life. The main focus here, as far as the material is concerned, is the titanium aluminum vanadium alloy, which is commonly used and which is the one we have performed experiments on, and then was later used as the base for the models. Based on these results, which had shown us exactly how it will deform, where to expect the fatigue cracks to initiate. And then we decided to start making numerical models, which would include a wide variety of different scenarios in terms of both weight and also different load cases, depending on how the patient would walk. So in this particular case, we had a total of 12 combinations divided in two categories, 4 different load cases: walking, climbing upstairs, climbing downstairs, and stumbling as the most extreme load case. And all of these were considered for 3 different patient weights of 70, 90, and 110 kilograms. So once again, we had a total of 12 numerical models, 12 combinations that we made in order to see just how much increased loads and increased weight could decrease the fatigue life of artificial hip implants. And of course, first we needed the geometry of the model, which is always very complex. This is the geometry that was, and also here you can see the actual hip implant that was used, the geometry for all the experiments. This was 3D scanned, and then of course it took some enhancements with special software so that we could eventually get this geometry, which we would use for the actual models. It was a bit complicated because of all of these holes and geometric irregularities, but eventually we were able to come up with a very good looking model. And I would like to thank my colleague Aleksa Milovanović for going through all that trouble. And now a bit about the numerical models, which for all of our researches, including some other combinations like static loads to determine if the critical location for tensile stresses would correspond to the experiment. But this is something we had performed in advance in part of other papers, so I won't go into too much details. This is an example of the model because all of them were the same. Here you can see the finite element mesh, which was made actually using TET elements. This is a typo, so please ignore it. With the initial finite element size of around 3 millimeters, which may seem a bit large for our calculations, but I'll soon explain why we started with such a big initial size. And here you can also see the loads and the boundary conditions. The boundary condition was fixed at the bottom part of the stem because this was the exact same way in which the actual hip was supported during the experiments. And the load was defined on the head, a downward facing force, which wasn't perfectly vertical, so we had to split it into components. So as you're not confused by seeing this here, its magnitude is shown here. This is just one of the many examples. For this case, we had 12 different values, which I will show you now. And here you can see how they were calculated, taking into account the mass and then, of course, the weight expressed in newtons. And these are the coefficients from the literature, each of which is related to one of these scenarios. And of course, the more extreme the load, the higher this coefficient. And these were the resulting forces. You can see that there is some very big differences between, for example, the maximum force here is almost 4 times greater than the walking force for a mass of 70 kilograms. And here you can also see the material properties defined for all numerical simulations for each model. These were the same. The yield stress was 780 megapascals, and the ultimate tensile stress was 860. This was determined experimentally at some point. And here you can also see the Paris coefficients, CNM, which would later be used for the fatigue simulations. And here is a more detailed view of the finite element mesh around the crack. This is the crack, which I think, if I remember correctly, had an initial depth of 1 millimeter, because this is what we usually, when we don't have this information, we assume the smallest length that can be determined using non-destructive test methods. So That's why we selected 1 millimeter, but that can be easily changed if there is a need to do so. And a bit about the actual way in which ANSYS does these simulations. Unlike the classical finite element method and the extended finite element method, ANSYS uses something called smart crack growth option, which is a new and advanced methodology that constantly refines the mesh and reduces the size of the elements around the crack with each growth. And even though the extended finite element method doesn't do this, smart crack is actually faster and more efficient because of some new advancements, but I won't go into too much detail about it. I'll just confirm that having worked in both Abacus and ANSYS, smart crack growth actually is faster and more efficient. And here you can see the crack which will be selected for the smart crack growth. For some reason, ANSYS always insists that you need to put a custom coordinate system in this crack and position it so that the positive direction of the x-axis goes along the direction in which you expect the crack to propagate. And also using smart crack growth was the reason why we decided to choose the tetrahedral elements, because they are the only available option. Although in this case, because of the geometry, we would have selected them anyway. And here you can see that the option selected for the crack growth law was the Paris law. You can also choose static, but we didn't need it for this case. And of course, the well-known Paris law equation, which the ANSYS software uses to determine the number of cycles and also stress intensity factor, because those were the two parameters we were looking to determine in this case. And here the overview of the results, the number of cycles versus crack extension diagrams. This is the walking load case, the best one with the lowest loads. You can see that the shapes are very similar, but the number of cycles, of course, decreases with an increase in weight. It starts in millions and goes down to a little bit below 400,000. And you can also see the stress intensity factors here, how they also slightly increase in weight. There is barely any difference between these two, but the fact that this one has increased more noticeably suggests that this model is much closer to reaching critical crack length or the unstable crack growth part of the AN diagram. Now for the downstairs load case, this is pretty much the same story. Once again, an increase in weight causes significant decreases in the number of cycles, although the shape of the diagrams remains the same, because throughout the calculations, all of them used a total of 14 load steps, and I was approximately aiming for 2.1 millimeter crack length in this case. We would have done it all the way to the critical crack length, but unfortunately didn't have the time, so we'll leave that for later. And once again, the stress intensity factors. This one, it was extremely low. I'll get to that point later because it was really curious and didn't expect it to happen. These are already showing an increase compared to the previous case. And now for the upstairs load case, which has loads which are only slightly higher than the previous one. So of course, the number of cycles will also decrease slightly, while the stress intensity factors, you can see, have also increased by a couple of hundreds of megapascals by millimeter times millimeter square root of millimeters. We always use the units with millimeters because our crack lengths are assumed to be in millimeters, so there is no point in converting it in meters, only causing additional confusion. And of course, the most extreme stumbling case, here you can see a huge decrease in the number of cycles. Now it's not millions, it's barely 100,000. And with the weight increase, they go even below that. Of course, the stress intensity factors have also increased considerably. These are already very extreme values. I mean, all the values exceeding the fracture toughness. And okay, here is an example of a video you can make to watch how the crack propagates in real time. So you can see how the stress intensity factors change along the crack front. You can also do this with any other type of results, if it was stresses, deformation, whatever. Okay. So once again, this is just more of a demonstration of what ANSYS can do and how you can get some very nice pictures and videos out. But so here is the overview of the results in the form of tables, so you can better see just how much the results have varied. Like I said, our crack extension for this case was 2.1 millimeters, which is probably a couple of tenths of a millimeter short of the critical crack lengths, which means the total crack length was 3.1 millimeters, because what we shown previously wasn't crack length, but actual extensions. To get the total length, you would need to add that 1 millimeter of initial crack length, which we assumed. And now let's see what we concluded when we compared these results to each other. Of course, we did expect the walking load case to be the most favorable, highest number of cycles, longest fatigue life, lowest stress intensity factors, and the stumbling to be the most extreme case. And this is the result which we have gotten. And like I said, the stumbling had a significantly lower number of cycles, much more noticeable than the rest of the cases. And what was interesting here was the difference between when going upstairs and downstairs. The difference in cycles was around 20%. And when we did some similar calculations with slightly different weights for another part of the research, the differences were also around 20%. So I guess these models definitely work. And as for the stumbling, even the lightweight case with 70 kilograms resulted in a force that was much greater than any others. You can just a second. You can see it here. It was almost 5 kilonewtons, and the next one was barely over 4. So it is pretty obvious why these cases were far worse than any of the rest. Now, as for the decrease in fatigue life, we see that the extreme cases with stumbling decreased it by almost like 20 times, from a bit above 1 million to 50,000, which was something we have expected. And for all 4 load cases, increasing the weight from 70 to 90 kilograms would result in around 40 to maximum 44% decrease in the number of cycles. And going from 90 to the maximum weight of 110 kilograms, it was around 35%, with the exception of the stumbling, where it was 31. So most of the values and the decreases were proportional, which was expected, since we still didn't make it into the unstable fatigue crack growth region. We will see if this will affect the results once we have the full models. And now, as for the stress intensity factors, we also see there is a very wide range from 2,358 to as much as 7,356 megapascals times millimeter square root per millimeter. And for the walking load case, I already mentioned there was very little difference between 70 and 90 kilograms, but the 110 kilogram model already showed an increase, which was similar to what happened for the walking upstairs model and the stumbling cases, where the increases were ranged from 25 to 30%, and an increase to maximum weight resulted in stress intensity factors increasing by 27 for the upstairs case and 17% for the stumbling case. And now the downstairs case was different. As we saw, it actually had a lower value than the walking case for 70 kilograms, which was pretty strange, especially even if we account for the small differences in the crack extension. Those were the order of magnitude of 100 part of a millimeter, and should not have affected the result, as they didn't for every other case. And all of these models were identical, same mesh, same boundary conditions. It was just the same Paris coefficients, material properties. It was just that the load was changed. So I'm really curious as to why exactly this model in particular gave me a much lower value than expected, since the remaining 11 all made sense. So in conclusion, this was the initial work involving the fatigue behavior of hip implants made of titanium, aluminum, vanadium alloy, and the 2 different parameters were considered: the weight of the patient and the load case scenario. So the goal was to compare these models to each other in terms of stress intensity factors and also number of cycles or fatigue life. And well, it will mostly confirm what we already expected to obtain, that walking was the safest load case and the stumbling was the worst. And furthermore, another important information we got from this is to know, when we continue this research, which of the models we can exclude from it, because there wouldn't be a lot of sense. For example, for the stumbling, which is, of course, very extreme, in the final case, it was like 50,000 steps, load steps. So that would mean that if somebody was to constantly trip and fall down, their artificial hip would last around maybe 2 weeks. So that's and since our usual results are in the millions, or at least hundreds of thousands, there is no sense in pursuing this any further. And we had that one anomaly with the downstairs walking case for 70 kilograms. And so for the next steps, like I said, we will extend these calculations to go all the way into unstable crack growth. So each of them will have a different number of steps until these values are reached. And then we will finally have the full results. We will try to get them by the time we submit the full paper for the special issue. So thank you for your attention. But just one more thing. Now it's time for a little bit of propaganda. Some of you may have heard that we are organizing a conference, the SCSIS Conference on Structural Integrity in Belgrade at the end of November 25th to 28th at the Hotel Metropole Palace. So, of course, all of you are invited, and we're looking forward to having you as our guests if you can make the time, or at least find somebody else who can come to the conference. You can also find more information on the conference website, www.bccsi2025.com, and I believe we have some flyers that we are supposed to distribute. Okay, so that's all from me.